Just firstly, just as an acknowledgement, thank you very much to the conference organisers for the opportunity to keynote this session on industrial applications. As the title suggests, this one's about something more detailed, looking at the manufacturing side and the potential for AI and ML techniques to be applied. Just a bit about me. My name is Chris Leung. I'm an academic working at University College London. I hold a post of Associate Professor in Architecture at Bartlett. My background's in architecture and the construction industry, and probably the last decade or so I've been in applied research engineering. The bulk of the research that I do has been around industrialized manufacturing for the AEC sector, particularly just by direct practicing of design for manufacture, assembly, disassembly, and end of service material recovery and reuse. And really all of this has been through end-to-end work on small scale demonstration projects. So the sorts of things that we do is everything from initial sketch manufacturing processes to in-use monitoring, data collection and analysis. Most of the projects that we do, they're kit of parts and they are fully functional. So we get involved in all of the aspects from the design, engineering, manufacturing and monitoring capabilities. Have I frozen?
Slightly, but it seems to be loading again.
Oh, did I freeze?
You did.
There. Just go back a slide if I can.
Okay, sure.
There we are. Yeah, so pretty much everything involves some level of direct engagement with manufacturing processes, and that's really at the center of this. I'm an active member on the UK National Standards committees. I've got particular interest in the Technical Product Realisation Group, that's the TPR 8-1, and of special interest in additive manufacture. And just a quick plug for publication that came out this month, just to illustrate the current work, which has been around four-dimensional additive printing standards and development of exactly what I'm going to talk about today, but in the four-dimensional realm at a small scale. Just for context, so in a bid to consider the potential benefits for the construction sector from the adoption of information standards that were developed for use in industrialized manufacturing to specify the manufacturing requirements on a product-based approach for the delivery of buildings as a kit of parts, the role of AI and machine learning techniques applied specifically to the machine readable data in the digital technical product specifications is going to be considered here in very much in outline. So this assumes a component-based approach, and just to signpost a previous keynote that I was invited to give, titled "In Search of a Dialogue for Manufacturing Conformance" back in 2021, seems like an eternity ago. It was a review offered to the DCIO community about some of the information challenges in construction. And specifically, it tried to make the case in favour of the adoption by the AEC sector of information standards for the specification of the allowable deviation in dimensional size and tolerance and geometric form for functionally critical features on components that have been developed for industrialized manufacturing over nearly 100 years since the 1930s, and that's what was presented. And really just to say that decades ago in the 1990s, the UK government commissioned a report into the perceived failings of the construction industry that identified these often cited key characteristics that were evident in other sectors, but that seemed to be barriers to success in the AEC sector, namely standardization, prefabrication, and pre-assembly. So it's this kind of approach, very much everything made off-site and installed on-site, as distinct from constructing from individual raw materials just on a site. But this whole approach does acknowledge that construction is complicated, and the analysis offered by consultancy firms, for example, McKinsey, from the evidence they've collected suggests that an approach where you use construct on site continues to suffer from low productivity and low, if any, improvements in production efficiency that have been evident from the data that they've collected over the last 20 to quarter of a century, 20 years to quarter of a century. And of the many faces on the prism of challenges to deliver a construction project, the quality information that expresses design intentions, particularly produced in the very early stages, is identified as an opportunity area for AI ML techniques to be applied to leverage value if the terms of reference can be expressed and performance metrics that reflect real world value can be identified and quantified. So overall, this is a standards-based approach working towards transparent and non-proprietary tools for use in a workflow. So reference is made at each step to read, understand, and apply the International Standards Organization ISOs so that the data represented and the rules for interpretation are documented and are as clear as possible. So at some point, a project reaches the building and assembly stage, and the reality of this usually hits hardest when the necessary methods and processes for delivery are either not well established or are entirely absent, poorly understood, unpracticed, uncertain, not systematized, and where there's a lack of the requisite skills to undertake all the processes needed. But it is acknowledged here that buildings are not cars, and the market demand and consumer characteristics for a home or an office are not the same as for those for a car or an aircraft or a mobile phone handset. And also acknowledging that buildings generally last much longer, they generally represent a far larger capital asset and the financial commitment than purchasing a car or a washing machine or upgrading a mobile handset. Nonetheless, the view offered here is that the delivery of buildings, if they were approached more like the delivery of products in the way that aerospace, automotive, medical, white goods and defense manage information for products, then some of the advantages and benefits suggested here might be gained. One of the key considerations in trying to find an appropriate level of abstraction to apply these ideas, and this is just offered as one jigsaw piece in a much larger puzzle of the AEC sector's challenges, is that there's a focus on manufacturing information at the component level that can be expressed in a machine readable form. As such, the terms of reference are in the portion of the value chain where the values of parameters and variables exactly at the point of production for manufacture, both the processes and quality control metrology, that are the most relevant to the outcomes and that can be directly accessed are the ones that are used as the terms of reference. So calibrating an appropriate level of abstraction to the range of spatial scales is considered a really non-trivial challenge, because while identifying and reviewing the existing standards for dealing with tolerances of buildings, the first bunch at the scale of a whole site and survey information at the scale of a building and at the scale of a building component, these are substantially different from those that are used in engineering, where, for example, in the technical product realization standards, there's a much more rigorous framework for describing what needs are. And this also, I think, plays to the paradox of working in a CAD system at scale 1:1, where you have a nominal CAD model and you do a straightforward orthogonal projection of it. But you have to recognize that real materials, actual substances, and the processes that put things together, they whether it's joining, fastening, or fixing them into pre-assembled modules, they all either exhibit or impart variability in dimensional size and or tolerance and geometric form. And this is really one of the threads to pick up, that a way to do that is to use model-based definitions, which is the digital representation of manufacturing requirements. And these have been standardized in ISO 16792. And essentially you're applying a language onto that otherwise nominal, mathematically perfect and geometrically perfect form. And this can be done in terms of datums and flatness, in terms of theoretically exact dimensions, in terms of perpendicularity, in terms of a datum system and other measurements, in terms of parallelism. And you can build up a complete specification for the location, the allowable variation in dimensional size, and the tolerance and geometric form to completely make a part testable that allows for deviation and focuses on the functional and critical features of the part, which are usually where things join. So model-based definitions are machine readable. They do have a syntax, and to an extent they have rigorous rules for interpretation. So and it's an open international standard. It's non-proprietary, and two file formats at least exist for trying to take the model-based definitions, which are those, I would say, metadata attached to the nominal model, and preserve them in an open standard that can be read by processors downstream, obviously through the whole of the value chain. Particularly, I draw attention to QIF, which stands for the Quality Information Framework, which is a very extensive framework. It's in some ways akin to the standards which I discussed yesterday in the first session. But the reality in trying to apply AI and ML techniques, of course, is that you need encoding schemes to represent either genotypically or phenotypically the information that's embedded in the file. So particularly the model-based development, the model-based definition, sorry. And the strategies for doing this really hark back probably to the 1980s, 90s, and early noughties, when there was a huge amount of work in for example, referencing John Holland and others who wrote some fundamental texts on using genetic programming, genetic algorithms, and other population-based evolutionary computation techniques. And obviously, the key thing is to select appropriate evaluation criteria. What does success look like? And this is where I think there's the key opportunity of trying to couple the manufacturing requirements through the whole of the process, and linking them to the trade space that, as a design for manufacturer practitioner, you'd be thinking about the competing pressures for time and cost and equipment availability and skill level. And this provides a framework, I think, for doing that, for trying to couple the actual description of the functionally critical parts and just putting precision where it's needed and not everywhere. Sort of stop treating CAD models as only nominal, and doing so at an appropriate scale. But there are lots of challenges, and I think construction being as messy as it is, perhaps one of the fundamental one is when and where in the process. So process meaning end-to-end, initial descriptions, initial sketches, survey information, everything that you can find out about the available manufacturing processes and their respective criteria for time and cost and so on. How can this be connected to the functional specification and at the level of detail that's been described here or suggested with model-based definitions? And how is this at those two scales of tolerance, those of building sites, buildings, and building components, with the industrialized manufacturing world, which is much more precise, and whilst easier to achieve in a factory, very difficult to potentially always match to the tolerances which can be achieved for site constructed components or site constructed infrastructure, thinking particularly of primary structure, foundations, and so on. So lots of challenges are at reasoning on sort of where to put the needle in with this, and what's most important, and where, by how much, and also when. And this doesn't even get to the point of a much more, I would say, difficult process of how tolerances need to accommodate change over time. Structures that may settle, that whole 4D dimension to this consideration. Some development paths, though, are offered for really just as a thought provocation, that development of lightweight inspection models, not necessarily using the same framework as happens in manufacturing, to metrology, to quality control and quality assurance procedures, but scaled up to the means that you have for a construction site and the slightly different scale in achievable tolerances. And also, in general, the adoption of product manufacturing information standards and the preparation of production information and the preservation of this through the value chain, from early stages all the way through to potentially O&M manuals and obviously with an eye towards material recovery and reuse at the end of service life. Incorporating design for metrology within the workflow. So in RIBA work stages, there's one eye again towards how you get feedback at the end of the project, but in a systematic and quantified way. And obviously, as a general research interest, heuristics for the efficient capture of the values of process parameters and variables as part of quality assurance procedures. I think there's a tendency, anecdotally at least, that you collect far more information that's actually useful. You sort of collect information where you can collect information, and I think there ought to be work done on trying to find the most efficient way. And what rule bases would you apply as to the mode of collection, the location of collection, the frequency of collection as a project progresses? And generally, overall, as a parting remark, that continue to promote greater use of existing standards and awareness of them, which is the reason for quoting them on the slides everywhere where I think it's relevant, and particularly data sharing, use cases and worked examples. So I'd just like to take the opportunity to ask any delegates working on small scale projects if they're interested in considering putting forward potential use cases for some of the ideas that have been discussed. Please get in touch. These are my institutional contact details, and thank you for your attention.